Our exceptional speaker of the evening has 14 years of experience and was formerly an alumnus of Techstars as co-founding CTO of Full Contact. Please welcome the CEO of AgilData, Lynn.
So this is a kind of riff on we got to preview this talk over at the Cloud Expo earlier this week, and which is nice because I got to see what worked and what didn't. There's a much larger format there, so what I have to do is I have to hide behind the screen and then let you guys watch a brief video. All right, let's go here.
Shapeless, like water. Now you put water into a cup, it becomes the cup. You put water into a bottle, it becomes the bottle. You put in a teapot, it becomes the teapot. Now water can flow, or it can crash. Be water, my friend.
I was going to come on stage while that was happening. It was much bigger. But I like Kung Fu. I studied Kung Fu for quite a while. For those of you that want to get into Kung Fu, there's like a really new, awesome instructional video that came out just recently. It's made by some Swedish guys. It'll teach you just about everything you need to know about Kung Fu in less than an hour. It's like 30 minutes long. And it has a cameo from David Hasselhoff. So I recommend that you check this movie out. And then I'll talk about why we're talking about Kung Fu. So Bruce Lee, as you know, really was the pioneer, the inventor of Americanized Kung Fu flicks. Right? In addition to being a fantastic film pioneer, he was a martial arts pioneer. He invented a brand new style of martial arts called Jeet Kune Do. It was patterned after Wing Chun. Really, it was a huge influence on how the westernized world started applying martial arts. You know, it was a massive, massive benefit to our society that we pay attention not just to what we're doing and thinking about, but also our bodies and how we interact with the world, in addition to not getting beat up all the time. And his comment about water is interesting. For those of you that study Kung Fu, it probably makes sense, but if you haven't, it's all about when something is pushing on you or something's hitting on you. If you're like water, you get out of the way of water. Water yields to incoming force. Water is supple. If it gets out of the way, it becomes what it's placed within. Trip on this if I'm not careful. Water is this amazing thing that really is formless, as he says. It does nothing. But it can also be rather powerful. Water will get where it wants to go. You can contain it, but as long as you can contain it, it has shape. If you're not containing it, or if your container isn't perfect, then water will go down as fast as it can, and if you're caught in the way, it can either damage things or it could generate power for you. It would be extremely useful. In that sense, water's ability to transmute itself, to change itself in response to the obstacles in its way and get where it wants to go, is an interesting metaphor for agility. Water is very agile. It will go where it needs to go. It will get out of the way of something, but it's not going to stop going where it needs to go. And I thought that was kind of neat. I thought it was kind of a neat parallel with this idea of being agile with our software development process. I'm not going to tell you anything you don't already know, but this is some slightly old slides, and you're here in ThoughtWorks, who are pioneers in this area. We're like 14 years into this Agile development experiment, right, that has really revolutionized kind of the way we've been building software. It's shortened our software development cycles. It's reduced our waste. We've gotten feedback far earlier in the development cycle. So I think it's fair to say that there's been tremendous progress by implementing Agile development and by building software that we ship earlier, that we expose to the market earlier. There are quite a few principles that came out of this. You don't need to read the principles. You probably have them memorized, or some of you probably have them tattooed on your back. I don't have those tattooed on my back. The interesting thing about this is keeping things simple, right? Shipping things early, getting feedback often, and more important, it's adapting to change. Adapting to change the way water does, being responsive to change, and recognizing that software can't control the world. It actually has to react to the world. So we've made incredible progress in this regard. Right? But it's not over yet. The mobile industry is continuing to grow. You pair that with the IoT industry, we're looking at even more need to make our processes ship faster, to be more reactive, to be less latent in our processing. Right? You look at what Gartner has to say. I'm going to throw the businessy stuff at you, right? not so long ago, Gartner's still telling enterprises, guys, 14 years into this, Agile development is essential to reacting to the explosion in data and the explosion in clients that are going to be touching your systems. It's essential to be able to be more reactive and more adaptive to the market. So we're really good at this, right? We actually have made a lot of progress. But there's kind of this one thing that usually gets in the way when we're being adaptive. You guys might be able to guess it, but there's kind of a nice metaphor for it too, which is that we kind of stick our data into this thing that sits there on a server, maybe two of them, and represents all that we know about the world. It's our snapshot of the world, and if we don't follow good security practices or we write really immature code, we can get into trouble really quickly. Speaking of PHP, that kind of happened a few times in the last 10 years of my career where I had to go deal with that sort of thing. Thankfully, we've got nice languages that abstract away a lot of this injection scariness. But the database is the thing that is not Agile. You guys probably know who Mark Fowler is. In fact, I believe he is sometimes in this building. Lab off.
Can you just put it closer? Oh, way up.
Hello?
Yeah, just way up.
Way up. Any better?
Yeah. Don't dug into it.
We might need a little bit more gain, but I think I'm hearing something.
It's good. I can make it a little louder. It's almost in the top.
If you guys can't hear, then I can speak even louder, I suppose. Let's try that. So Martin Fowler says if you change the database schema late in the development, which is kind of an older way of thinking when there's late in the development, but even if you add features incrementally, iteratively, if you add those features, they tend to get coupled to the structure of the data, right? Whatever you're using to talk to that database often mirrors the structure of that database. And we've seen a lot of cool stuff about how to write software, right, that is less coupled to the database, right? Famously, ORM mappers, right, object relational mappers help a lot with that. Although for anybody who's fought with Hibernate, until 3 a.m., you know that that's not necessarily fun. So imagine how bad it is once you go into production. You've added all this stuff that's coupled to the database, if you're not careful. After you've gone into production, you change the schema, you're in even bigger trouble. It can be pretty frustrating, right? You might want to go throw a sledgehammer at something. Right? You might want to throw the database in the trash. You might want to reconsider your career choices when you are stuck in a situation and maybe take up, underwater basket weaving or something similar. Right? It really, reminds you of back in the day when, your Windows machine just kind of failed on you. I think that clicking was me walking around. Yeah, it is. Let's see if that'll work. So I'm going to talk about kind of how databases model the world and why we got ourselves into this mess. This came out of a talk I gave about keeping APIs up to date. My previous life was at a startup called Full Contact, where we took all of your contacts and synchronized them into one place for you and kept them automatically up to date across a whole bunch of different address book sources. We had to deal with a whole ton of external APIs, and this whole idea of, is that API out of date? When was the last time I queried that? Am I pulling this other thing? What was the format? Are their clocks the same as our clocks? And that's a situation you have to deal with when you're going over broad WANs that might be on the other side of the world. It got me thinking about this idea of time in databases. We tend to think of time as this arrow. Right? We're all imagining that we could go forward in time, and we're doing that without choice. And then if only we had the most amazing technology in the world, we could go back and really hurt our brains with the paradoxical situation there. It's really like this idea where we just think of all we can really experience is the past. Really, right now, you guys are experiencing the past, right? My image, the light coming off of me, and the vibrations hitting the air molecules are traveling through, hitting your ears, getting converted into impulses on your nerves. That hits some receptor in the back of your head, right, far removed from your frontal cortex up here that actually can figure out what that might mean. That takes quite a few milliseconds for you to understand what I'm saying. So the fact that you're hearing me is actually quite a bit after I thought I was saying it. Right? And that's completely irrespective of whether or not the light took some time to get to you and we get into relativistic physics. But it's interesting to think that like we as humans experience the past. We don't even experience the present, right? We tend to think of moments as these points in time that have this absolute quantized timestamp on them, like a movie reel. And we tend to think of our systems in the same way. We're trying to think, do I have a transaction at this timestamp? We think about what the current state of the system is. At the boundary between the past and the future, our mental model is that the present sits somewhere in that kind of weird, blended boundary that we don't really understand and we can't really experience. So the interesting thing, not to get too metaphysical on you, is that like unless you've been studying yoga for years and you've disconnected your like mental chatter from the world, you can't really experience the present. You're always reflecting on it as a human. As a system that's trying to model the world, it can get a little bit more interesting because we try to perceive this like present state of the world, this idea that right now our system is like X. It represents the world as it is now. But if now doesn't exist, it's really just a sequence of events, a sequence of mutations to the world. If you could model every single particle in the world, notwithstanding the probabilistic nature of quantum physics, you could hypothetically have a deterministic system that could replay reality. But you can't. And the funny thing about how important time is to people and how interesting it is when systems are out of date. It's a pretty funny thing that hit the news a couple years ago. The Federal Open Market Committee met and they changed interest rates. And they're very, very careful about when they tell people that the interest rates change, because that piece of information has some pretty significant effects on what trading behavior does. And if you happen to get the information and you're here in New York, it's kind of like more or less 0 milliseconds after they announce the information. If you are in Chicago, I believe it takes 12 milliseconds, don't look me up on that, for light to get from New York to Chicago, something along those lines. So if you saw some trades entered from Chicago after 5 milliseconds, then there's probably some foul play, right? The sensitivity of time and the ability to actually record that resolution in a database is really important for us to think about how we actually model what is now in a system. The bottom line is that every database you use is always out of date compared to reality. If you enter a transaction in a bank record, it is only as good as the last time you looked at it. Right? You might not have refreshed your bank balance on your phone. Right? I showed up on Monday and managed to take an Uber all the way over here with my credit card, and then I got over to the hotel, and the hotel was like, your credit card's declined. Something happened, I didn't know about that. I could have known about that if I had a continuous stream of updates saying that my credit card company was like, well, you haven't been to New York in a while. We think this is fraud. So I had to call them up and deal with that. My perception of the world was out of date. If I had a database that mirrored that, it would also be out of date until that push notification, if I was lucky, got from that system to my database. Our data is always out of date. And as system designers, we need to try to combat that and be more agile with our databases. This like really old quote from Darwin. It's applied to biology, but it also translates into companies very well. The most competitive companies are the ones that are best able to adapt to change, and not just change internally, not change to whether or not you understood something, but change in the markets. This gets down to like an Eric Ries type lean startup idea, where you have to be able to respond to the market, where you develop this inertia in a company. And that inertia is not just human inertia, it's systems inertia. Your database is hard to change. That could put your company at risk. Bottom line is that the database must be as agile as our processes. And it usually isn't. It's usually, especially if you're dealing with a relational database, it's this thing that you put a bunch of structures into, and then you insert that data into those structures, and it probably just goes there and stays there forever, and maybe it's lucky if you query it. Right? Probably grows out of control, and then you have to rotate it out, or deal with it in other ways, and then maybe if you do query it, your index is really slow because you made this giant B tree and now you're suffering from that. The database should be as agile as the software development process. We continuously deliver all the way up to a point, at which point it's a little harder to keep the database up to date in production, right? What makes it agile? Well, one thing is trying to keep it up to date with the software, and there's some pretty awesome tools that help you with that, right? There's a fantastic book that came out quite a while ago talking about refactoring databases. It applies the concept of refactoring to the database. So if you know refactoring for your code, it's making structural changes to the code that do not affect the functional requirements of the software. You do that to make it faster, or you do that to make it easier to work with, right? But if you could apply that same concept to databases while they're running, you could be more agile. And there's some very nice tools here that work in a lot of different platforms. But that's really not the only thing that makes the database agile. It's more than just schema migration. What then would make a database agile? The bottom line is that data is complex, and that thinking about data is complex and modeling it tends to be complex. And we developers, myself included, have this really bad habit of looking for very clever solutions to certain problems that after you've implemented those solutions are another system or another cluster for your operations team to deal with. Right? You've got this other system that now you added this other one. It's kind of like that additional standards joke where you say you're complaining that there's 13 competing standards, and then let's get that one standard to unify them all, and then guess what? Now we've got 14 standards. Right? Bottom line is that your database should be as simple as you can possibly make it, and the solutions you provide should be as simple as you can find. Right? It should be simple for everybody that touches the data, the developers, the DBAs, right? And the operations people especially. And then the users, if you actually have analysts touching that and querying that. It should go without saying that your data should be scalable. The database should be able to run on more than one machine, and not just for resiliency purposes. There are certain cases where the data is not that large, where it's super high performance, high frequency data, and it makes more sense to keep it all in the memory of one machine. It's especially maybe not a GCC'd or a GC'd, that's a funny Freudian slip, a GC'd system like Java, where you're trying to do garbage collection on objects. If you're doing that at super high frequency, you might be able to get away with just one machine, right? Where you're really more interested in optimizing, cache lines. What did I do? I did. Well, you have to squint, right? You have to squint. We're optimizing cache lines inside of one database, right? We're inside of one system. We're trying to do things faster, and it's really all about microseconds. But if it's not about microseconds, if it's more about milliseconds, and the data is so large that it would never execute correctly on one machine, then you have to sort out a way to scale that out. And as our data grows, as we add more volume, people querying it, as we add more actual velocity, meaning more and more showing up at any point, how do we keep that scalable? We have to be able to find systems that scale out cleanly with a simple model. My personal belief is that you should focus on streaming. You should model your data as streams. And this gets close to the water concept. Water flows in streams. What does that really mean, though? Streaming is a kind of an amorphous concept. It talks about change data capture, or reactive programming, or event sourcing, or a number of these things that are all built towards the concept of reacting to events and replaying events. And that's the way I think of streaming. I think of streaming as events happen, and we react to them as they occur. We don't stick them into this repository and then come in behind with this batch processing that maybe takes a minute or maybe takes 24 hours. And batch jobs tend to do that. Sticking it in the table is the beginning of that problem. That table is that static repository that you've stuck the data in. And now the only way to get it back out is the batch job. But really every insert into that table is an opportunity for processing. And what sucks is you don't want to also write your insert and write your processing in the same place, because you don't want to slow down the user experience. You want to ingest the data, make sure you have it, make sure it's reliably consumed, and then generate insights for your customers or data-driven features that sit in your roadmap sit on your application that people can access downstream in a predictable latency. So the way we think about that, right, is collecting data from a number of different sources, any number of different sources, and applying streaming transformations, streaming filters to that data as it comes in. And this isn't just doing this against a single table, this is against all the different kinds of data you could have. If you can think about it or try to model it in your system, either via some combination of message queues or message brokers of some sort that are distributed, you could actually build downstream views of data that are queryable as if they were tables, but they're predictably generated, and you can reproduce them in the event that you want to change your mind. You can be agile with that schema without affecting the ingestion pipeline of your application. Near and dear to my heart is, how do you actually process this stuff? How would you stream stuff? How would you join it with something that you might already have that is more of a static view of data, static repository of data? I think it's incredibly important to realize that we're sitting on a gold mine of talent. I'm a NoSQL fanboy, I'm a functional programming fanboy. You know, I've stayed up far too late learning Clojure and Scala and really loving those languages. But I'm possibly in the 2% of the bell curve that actually will dedicate that time out of all developers that are going to do that. It's great that I'm geeky. I love being geeky. But some people also want to go home and have a family, right? I don't have a family yet. Probably won't be doing that till 2 a.m., right? When I have kids to keep happy and when I want to spend time with them. But everybody that has been touching a relational database for years actually can read this and have a decent idea of what I'm doing, what I'm talking about, without having to go to a class or without having to pull in some consultants to teach you how all this works. Because big data is complicated. Big data involves a whole ton of tools, a whole ton of weird logic about routing things from here to there, right? And a lot of the tools in the industry right now are focused on making it simple. And I think the way to be simple is to try SQL first, right? Well, the problem with SQL is that it's usually designed to query static data. It's designed to query tables. But if you think of a table as a stream, if you prefer streaming, and you start with SQL on that stream, you can produce a graph of transformations, very similar to a quick audience participation option. Who here knows either Storm or Spark? Okay, that's pretty good, right? Quite a few. They're very cool open source projects which try to apply this concept. One of those two actually is trying to throw SQL onto that concept too, but it models your processing, a stream of processing, as a sequence of tuples, and a tuple is like a row in a database, right? A sequence of tuples are just flowing through this system, this abstract system we're talking about, and SQL merely transforms them. Those systems I mentioned express it as a graph of transformations where the tuples are flowing. You change this into one thing, it goes over here, you change it into something else, and eventually you make it queryable right via ordinary SQL for applications to present to users. How would this manifest itself in reality? This is like, imagine gaming, where you've got everybody making actions in the game, and you want to show a dashboard of who are the highest scoring players, and you want to keep that up to date within seconds and not within however long you can keep this batch process running. Right? Where that same idea of real-time analytics, right, or high-speed analytics, where you have to query it a lot, but you also have a lot of data. That happens everywhere. That happens in auto manufacturing, it happens in plant manufacturing, it happens in any kind of sensor data, it happens in any kind of user-facing web application where you want to offer a feature back to the user that is dependent upon either all of that user's actions or everyone else's actions, or doing multi-dimensional aggregates that you're giving them quickly. You can do this with SQL. You can apply windowed aggregates. You can join against other streams. You can join against static data. That's where it gets a little complicated, the stream-to-stream joining, because how long are you willing to wait for that other piece to show up? Right? But you can intelligently reason about that and set reasonable timeouts for rating on real-time data. And you can do it all with SQL. How would you do that? I want to talk about kind of an example architecture, and it is kind of customer, vendor pitchy, right? This is kind of how AgilData does this. Right? This is my company, and kind of how do we structure this for our system? How do we live these principles? For us, is that processing must happen next to the data. This is really not a new concept. For those of you who have ever used Hadoop, the idea is you write your Hadoop code, either via Hive, Pig, Java, go down the list, there's a whole ton of it. Right? Hive is SQL. It actually translates your SQL to this giant chain of Java MapReduce jobs, or now it uses this other thing called Tez. It's really cool. But the idea is it sends the computing to the data. The data's sitting there. It's sitting there at rest. You send the computing over to it. You scan down the data. You do your transformation. The same can be applied to streams. Processing must be where the stream is. You need to send the processing to where the streams are, so you avoid sending data over the network unnecessarily. How would you do that in a streaming example? If this is I'm just streaming, in this case, it's view data that's coming out of a view. It's just a view that I might be inserting into, and you're trying to stream out of that view as data arrives. In this case, my transformation is the simplest of all. It's a select statement. I'm transforming what might be a whole row of people into just an A and a B, whatever that is. It's an abstract example. But I'm filtering some subset of each row down to a little bit, right? So that maybe I don't need to deal with as much of it, maybe I don't need to load as much of RAM. But the point is you send the select statement to the data. You run that inside, in our case, inside a JVM that handles that and finds the data locally and runs it. You get that local execution. And by doing so, you're not sending data over the network, you're not going back and forth between networks, you don't suffer that latency penalty over and over again. You're scanning right through the data as fast as you can get it off a disk, or as fast as you can get it off the network. Interesting thing about views is a view is kind of just like a snapshot of a stream. It's a snapshot that you can either keep up to date by streaming into it constantly, or you can just put stuff in there and treat it like a regular database table. And all you have to do to run this in a clustered environment is figure out a way to partition it. And in this case, we let you define a partitioner. Right? Everybody seemed to know what UDF was, which is pretty cool. Right? We have partitioning UDFs. We supply quite a few of them, but you can write your own if you have specialized partitioning logic. And because in this case, this view has a person in it, which is different than like a traditional database. Actually, many databases, many relational databases allow you to define types, but it's kind of a lot of work to make it work. You have to recompile the database sometimes with whatever your UDF definition is. It's kind of interesting. We allow you to upload new data types into this and then co-generate high-performance interfaces to that then work with your user-defined functions. So if you really cared about what a person was, you can look at the ID of that person, or you can look at that name and partition by who knows what's going on with the person. It's all up to you to figure that out. It's great. It's very powerful, but it's very simple for the actual, line-level developer that's trying to figure that out. So I put this picture back in here because that's the way I think of views. It's a snapshot at a point in time that you put in. It does mean you can duplicate data, but you can shape the data properly for a certain query pattern. Okay? It's like denormalizing data. It's re-denormalizing data for different purposes, but usually that's kind of like a DBA's worst nightmare. But if you make it predictable, such that the data itself is not this thing that you're thinking of as this gold, this precious gold that you have to hang on to. It's just this thing that you've projected off of a continuous stream that you could always reproduce just by changing the functions you apply to it. It becomes very powerful. And the way to do that, the way to build a stream, and the way we build streams, is by using logs. Who here knows about database replication logs? Hands? Okay, good. That's quite a few. You have a primary database and you have a secondary database, and the reason there's a replication log, the first reason there's a replication log, is so if the master database in this case fails, you can fail over to the slave. You can send all your queries to the slave and not have any downtime, if you're lucky and you manage to fail over properly. But let's not talk about that. It's really more like, how does the data get from the master to the slave? And the cool thing is that databases understand this log concept, the streaming concept, very well. If you zoom in on what the log is, there's just some stuff in order. And those things are an insert statement. Create a new employee, right? Update an employee and pay them a lot, You sequence it in the right order. But you could replay that by any other machine, any other slave machine, and you can reproduce the same state. What if you could also apply a function to each of these along the way and reproduce a slightly different state? But you could replay that whole thing each time. Right? Reproduce that view that's then queryable. Right? You've shaped the data in the right way, indexed it in the right way for a different use case without affecting the ingestion, without affecting the inserts at the beginning. The way to do that is you have that stream input, a write-ahead log in this case, and you apply functions to that along the way. Those could be user-defined functions. They could be arbitrary SQL. They could be what we call stream functions, which allow you to do kind of the functional equivalent of a flat map, if you've heard of that, right? It either takes in one row and emits 0 rows, filtering things out, takes in one row and emits 1 row, or takes in 1 row and emits lots of rows, like splitting up a string by comma. If you've ever tried to do that in a relational database, there's functions that we try to do that, and they don't really work. It's really hard to take 1 row and turn it into many. Some of them can do that, but a stream function in our case allows you to do that. Stream functions are relations. They are just like a stream. They are just like a table, and you can query them. You can query the function with other functions. And I know that might sound painful, but if you do it all with SQL, it's actually quite simple. And then what you do is you just optimize this. You run this as close to the data as you can by having a very smart execution planner that can figure out, where do I run this, where do I run that. I mean, this is just one JVM. If you have quite a few of them, you just connect this with a network out the door. And the other monitors started working. It's magical.
It chooses which slides it thinks are important.
It's judgment. I'm being judged by the technology.
It's a stream function.
It is. Yeah, this is good. Okay. In our world, you get reliability for this, right? And this model is very similar to some open source stuff as well, like Apache Kafka. You have a log for a given table. In this case, it's an example topic, which is either a stream or a view. If you partition that, in this case we have 2 partitions. This broker on the left, right, this JVM on the left, which might be on one server and this might be on another server, is responsible for the first partition, the 0th partition of the data for that given topic. The other one is the leader for the second partition, the first partition. I know that's complicated. Zero-based math is fun to talk about. And what's cool is this is a follower. It just replays that stream. It just reruns that execution somewhere else. Maybe a little bit later in time, but predictably later. And by doing so, if either of these fail, execution just switches over to the new leader. You find a new leader. And usually you don't have a simplified example like 2 of these. Usually there's quite a few more. And you get to use a nice consensus framework like Zookeeper or etcd or something like that to help you choose that new leader. And there's very nice open source libraries. If you wanted to build something like this yourself, there's very nice open source libraries that can help you structure this kind of code. Something like a Zookeeper combined with Apache Kafka or something, you can build something pretty close to this. When you put it all together, this is our branding marketing slide, right? Where we throw this up and it solve all your problems, right? This is more like the conceptual model of how this works, right? You want to be able to connect to third-party data stores. You want to be able to consume things from MySQL or SQL Server or something like that. You want to be able to consume things from message queues like Kafka or RabbitMQ. And you want to be able to produce that right back to those same queues. You have to play nice with whatever your company already has present. And then anything else that could produce event streams like that you wouldn't have thought about, like web servers where APIs are coming in, right? Anything where you're tracking clicks, something like that. Then as I mentioned, it'd be great if you could do user-defined functions and data types. You can customize this, right? So you're not just dealing with primitives all the time. When you deal with primitives, it's hard to do type checking in some cases because you don't know what you're dealing with. But if you could actually have a person object in Ruby or Java or C++ and compile against it, compile your user code against it, it's a lot harder to make mistakes. It's a lot easier to test. You want to do distributed stream processing, right? As I mentioned, you use that log-oriented approach. You want to version your database structures however you can. Now, the best, most common way to do this is based off of database refactoring techniques and tools. Things like Liquibase and Flyway and the way Rails Active Record will help you migrate a database schema. You want to be able to version the things in the database. If you're also uploading your code into the database, if you're uploading user code to do special things, you want to be a little bit more rigorous about that. You want to be able to track which version of what did I upload into the database, and more importantly, the bane of every developer's existence, what does it depend on? What is your code's dependencies, right? That's the one thing that will keep you up far too late, trying to sort out why mysterious bugs have shown up because you pulled in that like transitive dependency three libraries later that has now screwed up your runtime. You want to pay attention to that, and that can happen in a database just as easily as it can happen in your application. And when you build something like this, you want to provide an easy API for other systems to work with this. Now, this is a fundamental lower level approach. You're building data systems. So probably for high performance data, you're not looking at a REST API. You're not looking at the overhead of HTTP. You're not messing around with JSON in some cases. You want high performance serialization using interesting things like Google Protobuf or flat buffers, or we have this thing we're going to open source later this year that's a very awesome SQL-oriented serialization library. You want to optimize for throughput in these cases, be streaming, but when you do have latency-sensitive requests, simple JDBC or simple ODBC where the application just sends SQL and it says, hey, select star from wherever, where, hopefully not select star, not necessarily the best pattern. That allows you to plug in other things for your users like analytics platforms like Tableau and Spark. Allows you to plug in monitoring and management tools to really pay attention to all of this, like know, is it running? How is it failing? Where are the logs? You put all this together and you have something that is an Agile database. Now I want to introduce somebody else, and we'll take questions after this, but we brought along with us one of the founders of this company who, he's got a story about how he got around to this. But you might have, those of you might have been here before, might have seen Cory Isaacson present before. Very entertaining guy. He wants to share with you kind of his experience on building something like this in a relatively large company. So let me grab the mic here, and I'll get out of the way.
Great. So hi, everybody. So I'm Cory Isaacson, and I don't know if any of you came last year, but I was representing AgilData last year. So you might have heard me talk before. So now I have kind of a different role. I think I'm experiencing a midlife identity crisis now. So basically what happened is I met Dan because Dan was a customer of our company a few years ago. And anyway, what happened was that I went to this company called Risk Management Solutions, which I'll tell you about in a minute. I'm the Chief Technology Officer of Risk Management Solutions now. But I went to this company and I said, you know, we have this product coming out called AgilData. We'd love to see if you would like to try it. And they said, you know something about big data, and they said your technology might be good or might not be good, but because you know about that, we kind of have some problems. We'd like you to come look at it. And so I said, okay. And basically what happened was they had who's ever worked on a software project that didn't quite come out like you wanted? So they had a big one of those. You can read about it if you want to. So basically they had this problem project, and they said, would you come and look at it? And I said, sure, I'll come and look at it. And then I said, if our technology is a fit, then you can use it, and if not, fine. So I got involved there, and they basically said, well, could you do some consulting to help us, fix it and do it better? And I said, sure, I'm happy to do that because right now we're doing a lot of development, and I didn't really have to be that active, doing my day job. So basically, I started working there. And sure enough, I brought Dan in to help me because he actually, at a very young age, retired from full contact. So he basically did correct me that. What's that?
If somebody would have told me I retired.
And I said, you don't want to be bored, do you? So come and help me. Anyway, so Dan came and started helping me with this project to help figure out what to do about this system. And I'll tell you a little of the story in a minute about, it's a very, very big data problem. It's a very unique one. So anyway, he comes and starts helping me. And then I got to be friends with the CEO, and I fell in love with this project. And the CEO of Risk Management Solutions said, maybe you should come to work for us. And I said, well, I have this company, what do I do? He says, well, I don't know, how do you solve that? I said, I have to get another CEO. So I said, Dan. And so he became the CEO, and now I'm the customer.
Yeah, I don't recommend this usually. It's pretty intense.
So we completely switched roles. Anyway, so a little bit about my background for those of you who haven't met me before. So I've written a couple of books. One is called Understanding Big Data Scalability. That one came out earlier this year, I guess, last year or something like that. And then, but in 2007, I wrote a book called Software Pipelines. And Software Pipelines was all about what? It was all about modeling software systems as water. So that's kind of where this idea came from. Because it really is, if you have a distributed system and you want to figure out how to make it go faster and where the bottlenecks are, it's just like putting fluid through a pipe. It's the exact same type of problem. And if you model it that way, basically what I was able to do is take some very simple math. I have to tell you a funny story. Does anybody know RogueWave software? C++ tools? RogueWave? Yeah. So anyway, prior to all of this, I was the president of RogueWave software. So I spent a lot of time in Wall Street here, and I learned a lot of things from a lot of very smart people, including this idea of software pipelines. That's really I learned from Wall Street. But anyway, so we were working on this concept at RogueWave, and I said, we really need to be able to predict the speed of this distributed system we're building, and I would love to be able to do that, mathematically. So I went to my team and I said, how would we do this? And they said, oh, wow, that's going to be really hard. They said, it's calculus, you have to figure out latency and all this other stuff. And so I went home to my 16-year-old son at the time over dinner, and I explained to him the problem, and he looked at it and he says, Dad, it's just division. And it turned out to be true. He was really right. And so the whole book is based on a formula that he helped me develop, which is really a derivative of Amdahl's law, if any of you studied that. So it's really the same concept. But anyway, so that really got me going on this whole idea of distributed systems and distributed data, because I've been working with databases all my life. And I don't know about you guys, but I really hated developing database applications. That was my entire career, but it was awful. Because you could never get the database in the structure that you really wanted to make it fast and make it scalable and make it do what you wanted, right? It's always a pain. And so I said, there's got to be a better way to do this. And so through several years of work, literally it was about 8 years more work after this, we were able to actually come up with this concept for Agile Data and prove it, and it's really, really cool. So now, as the Chief Technology of Risk Management Solutions, I'm going to just tell you a little bit about our application and what we do. Anybody ever hear of RMS?
Yeah.
Yeah. Oh, I hope it was good.
I'm in insurance.
Oh, good. So someone in insurance knows who RMS is. RMS is the biggest catastrophe modeling company in the world. So that's what we do. So what do? Is we actually simulate damaging your house, like a lot of times, with a lot of different bad things. That's what we do. Like hurricanes, like Hurricane Sandy, for instance. We were, by the way, the closest catastrophe modeling company by far to predicting the actual claim losses for the entire insurance industry from Hurricane Sandy.
Wind, water, quake, fire, and terrorism.
That's right, that's right, that's right. We do anything bad that can happen, that's what we pay attention to. That's really what we look for. But it's interesting because it's a fascinating company. Basically, the founder is the CEO. He's been there for 25 years. He started the company when he was 19 out of Stanford. Brilliant guy, really brilliant guy. And he taught me about this, and I said, what's so important about insurance and catastrophe modeling anyway? And he said, well, look, if we don't do catastrophe modeling, an insurance company can't safely write insurance because they might go out of business. That makes sense, right? He said, if you don't have insurance, you can't build an economy. And I said, really? And he says, well, look at Haiti and look at Japan. They both experienced very, very bad earthquakes. Haiti was, what, 10 years ago, 12 something, a long time ago, right? And Japan was a few years ago, right? Within 2 years, Japan's economy was totally booming. Haiti is still in trouble from that earthquake 10 years later. Why? One had insurance and one didn't. And 75% of the world is actually uninsured. So it's one of the real reasons that there aren't economies that are thriving in those places. Because who's going to put money in if you have no protection for your house? You're not going to spend $1 million on a house that could just be wiped out, right? So it's a lot more important than I first thought. First I thought, well, this is an interesting kind of academic problem that I could get, have some fun with, but it's much, much more than that. So we have all these modeling PhDs, and that's what they do, is they basically study hurricanes or earthquakes or all these different types of catastrophes. And then what they do is they develop models that actually simulate thousands or tens of thousands or hundreds of thousands of those. And then they basically take insurance contracts and they run all these models against those contracts. And that's really what the company has done for 25 years. So now, it's a fascinating thing is RMS says, okay, we want to build, our software runs today on standalone servers at all of our customers. So it runs on a SQL Server database, and we have thousands of these servers around the world that are running from our customers. They said, we have these new kinds of models that can't run on a standalone SQL Server. So basically now we need a cloud to run this on. So I said, wow, this is really a big problem. And I'm going to show you just how big of a problem it really is. So there's a lot of challenges to risk management. So basically one of them is that historically as a company, we have been modeling real property. That's all we've been doing. That's what we've been doing the entire 25 years. So any kind of real estate, we figure out how it could be damaged, and that's what we do. But now we have customers that want to get into insuring all kinds of things. Maybe they want to insure light bulbs, I don't know. They can insure literally anything. Because why? Insurance is really just a contract. That's what it is. You could write a contract about anything. I could say I'm going to insure your wallet or something like that. If you were willing to pay for that, that could be a market. So insurance companies are very interested in going after new markets and new parts of the world and all kinds of things like that. And so we have to be able to take what we call exposure, which is like a house or a person or something like that. Now we have to be able to handle any kind of exposure. So we call it extensible exposure, which means not just that I want to be able to model different kinds of exposure. What if I have a definition of a person, and you have an insurance company, you have more information than I expected, and you want to use that in your model, then you want to be able to extend my definition and use that. So now we have to be able to actually extend data types just like you can extend objects in Java. That's a pretty cool concept, right? Not so easy to do. There's very few databases that can handle it. You've heard object databases were kind of good at it, but not really great. So it was a very, very difficult challenge. So we had to be able to do that. On top of that, like I said, insurance is contracts. That's all it is. And so now if you're going to insure all these kinds of things, how do you actually model a contract so that a computer system can actually deal with it? Because you can make that contract do anything. So we wrote a language called contract definition language. We've had that for a few years, and it's really cool, and you can actually use it and put that together to describe any kind of contract. And then we have business hierarchies in the insurance companies. So really big companies may have many, many business units. And they want to break it up by business unit, or they want to see how they're partitioning out their insurance. Sometimes they sell part of the insurance to somebody else. That's called reinsurance. So they need to keep track of all this stuff, and they have to be able to report on it. And then now that we have all this flexible data, now we have to be able to exchange it because, again, I might take part of my portfolio of insurance and I might sell it to you because I don't want to take all that loss. And that's really what they use our models for, is insurance companies decide how much risk they want to take. And when they don't want to take more than that, they basically say, oh, that's too much, I'm going to sell it to somebody else and share the risk. And so this risk gets shared all around the globe in the financial markets eventually. That's really how it works. It kind of bubbles up to the bond markets, and that's really how the whole thing works. There are hedge funds here in the East Coast for sure that's all they do. Is they basically buy up these insurance policies. So it's a very interesting data problem. But the other is there's this concept called open modeling. And so we have long time made probabilistic models, just like I described. We take events and we basically apply those events to things, and we figure out how much it's going to hurt those things. We put it against the contract, and we can figure out what your loss is going to be. That's historically what we've done. But we found out that, well, first of all, there are other kinds of models. There's simpler models called accumulation models. We don't have to worry about that. But there are actuarial tables. Probably a lot of you have heard of those. That's how insurance always worked for years and years. So those are kind of models, too. We also have pricing models that people develop. But there's also this new thing that our model development team came up with called HD models, right, or high definition models. Why? Because it's much, much better if we can do a model at a very, very detailed granular level. We can get much more accurate prediction of what's going to happen. And also, the geodata available in the world is much, much better. Like we have actually a flood model that goes down to a 30 by 30 meter grid. So we can actually tell if this room is going to flood versus that room. Literally how accurate those models are. It's pretty amazing, actually. And why does that matter? Because it's very possible that a house sitting here gets totally wiped away and the one next door is totally fine, based on the contours of the earth and the way the flood goes and all those kinds of things, how far the river floods or whatever. So these are very, very important characteristics. So anyway, so they one of the people who works for me pointed out that an HD model is high definition, but they said really an HD model stands for huge data. And I'll explain why. So and then we want to be able to provide models from anybody. So maybe some of our customers have models of their own. Maybe we have other modeling companies. Maybe we have third parties. Maybe academic institutions are now building models. Lots and lots of people are building these models. We want to be able to run any of those kinds of models, which is a very interesting challenge in itself. So now the problem is the model's no good. We have a new guy who's running the business unit that I work for, and he said, what is the point of having all this HD content if you don't have an HD TV? And so the point is we have to be able to do analytics to get anything out of this. We have to be able to see what's really going on. And because we have such granular data, we really should be able to do what we call any metric and any resolution. And that's really what we want to be able to do. We want to be able to say, show me what my risk is within a mile of the coast in this part of Florida for homes that are over $1 million that are made with wood frame construction. You should be able to ask a question like that and get an answer. Well, that all sounds plenty good, right? I mean, sounds feasible, right? Those of you who know about models know what I'm about to say now, right? So how does this actually work, right? Sorry for the bad formatting on the slide, but basically, let's say I have a portfolio and it's 1 million locations. I've got 1 million houses, and I've got 50,000 events that I'm going to simulate, 50,000 flood events or whatever. I have a 10% hit rate. That means every house might get hit 1/10 at a time. So that gives me 5 billion loss values. So I get 5 billion loss values out of that I actually have to compute. So that question that I just asked you has to go out of 5 billion loss values. Now that's from running the model one time. Okay, now imagine that we have HD models, which are actually much worse than this. That's why they're huge data. So now take that same 1 million locations, basically say that for every year, the way an HD model works is we actually simulate based on time. So for every year, we basically have 6 events, right? And we have 200,000 periods because we're going to simulate 200,000 times. Same 10% hit rate. Now we're talking about 120 billion loss values. This is gigantic. And I've seen some projections that are much bigger than this and much worse. Now that's one model run from one customer. You can imagine that we have a lot of customers. I put this in the cloud. We're going to be doing this a lot of times in one day. And 1 trillion losses, right, at let's say a 4-byte float or an 8-byte float, it's a big number. It's a really, really big number. So the problem I was challenged with is how on earth are we actually going to be able to do this? And how can we actually run this in metric at any resolution? So what we did is we basically took the entire concept, and what we did is we turned it into a streaming platform using, of course, Agile Data. Right? That's how we did it. And I did, kind of bring the product with me when I came. So it was in my pocket, and I said we should try this. Anyway, but basically what we did is we basically turned this into a streaming platform. Because why? We basically have streams, which are functions, and views, which store things. We basically can have a function that is the model itself. Think of it that way. We can have another function that's basically reading or doing something with the exposure data itself. So we basically can have this stream of data that's actually flowing through our system, and we can take those losses and we can put them in a view. Now, it was a really cool concept. Using the SQL methodology to be able to do this, to define the streams, made our job so much easier that I'll tell you that we were able to develop things much, much faster than our own development team thought. I actually told them what I wanted them to do in 1 quarter. They almost fainted when I started. But I said, no, it's going to be okay. Watch. And they actually did it. They actually were able to do it because we could orchestrate it so quickly, and basically all we had to do was write the functions, and Agile Data pretty much did the rest of the job. It was really, really pretty slick. So, but we still had this really giant, huge data problem. I call it the big data explosion. Most people have big data, they want to do map reduce and reduce it to a few values. We take a pretty big set of data, which is the exposure data, and we expand it into a huge amount of data. That's what we actually do. So I told the CEO, I said, I don't really know how I'm going to do this, but I'm going to figure it out. And I can tell you that it took me about a year to be able to do this. But because of Agile Data, we were actually able to make some very, very specialized data formats and some other tricks that we were able to do with the math on how these things work and get it to be a reasonable size. I wish I could tell you more than that. I can't, because I have to shoot you, otherwise I'm too many people. But anyway, the point is we were able to do it. But the point I want to make about it is we had a very specific problem, so we were able to optimize it. But because Agile Data helped us, there was a lot of generic things we just didn't have to worry about, and we were able to focus on that one thing. And to me, that was really worth the whole process. Because of that, we were able to concentrate on that problem and really nail that problem. Because all the rest of the stuff was pretty much just plumbing, and we didn't have to really pay much attention to it. So our development team was working on the models, they were working on this one problem, and because of that, we were able to nail it. And so it really is pretty slick, and the approach we use could be used for lots and lots of things, and someday we'll make that public. It's really pretty neat, actually. So anyway, I think we are ready for questions. And there's 3 t-shirts left, remember.
Yeah, there's more.
Oh, there's more. Yeah.
Okay. And I can swap sizes too.
I have a question about
Hang
streams.
on. Before we move on to Q&A, I first want to give a great big round of applause to Cory Isaacson and Lynn. We have a little more than 3, so good questions get good t-shirts. Go for it.
Let's ask my question. We saw how specific stream is declared, like create a stream based on what you saw on SQL select whatever.
Right.
How stream is implemented?
You have to talk to Dan after about that.
Yeah, so the question is, how do you implement a stream as a select?
Yes, yes.
That's probably a
I
pretty
don't know,
detailed
wait,
answer.
I'm sorry, I don't know who this question is because you showed that definition, but you said you use streams. Therefore, but anyway, Cory, you can answer. I will appreciate in any case.
Yeah, that's a long way to answer. You would implement that in a variety of ways if you wanted to build this yourself. We've implemented one version. I can tell you how that works. It is a Kafka-style log that's on disk. It's something that tails that disk, right? Streams along it, and then uses our serialization library to make that available, and then applies your function to that, and then sends it back out on another stream. So obviously the answer is a lot more detailed than that, and I'd love to talk more about that, but I have a feeling we'll cut into other questions.
Okay, next question.
It sounds like a streaming compute platform doesn't have persistence on this, right? How does it sit next to Spark Streaming and Spark SQL?
Sure, I want to make sure I understand the question. The question was, it sounds like a streaming platform doesn't have persistence?
Streaming compute platform without persistence there, right? It sounds like
I
the
see.
streaming Storm kind of computation in a cluster.
Sure,
There's
so
no persistence there.
in Storm, the question is, in Storm there's no persistence baked into Storm off the bat, right? So is this something that there's no persistence? Because like our specific implementation, AgilData, is based off of on-disk logs. There's tons of persistence, right? So it depends upon, are you talking about persistence for failure mitigation, or are you talking about persistence for queryability, right?
So once you're actually streaming in, you're doing your calculations, right? Is the output also streamed out, or is it actually persisted on disk somewhere?
The best part is that's entirely up to you. Oh, we have a picture. I like it. And I'd love to talk in more detail about that. That's great.
Okay, next question.
So basically, the views, just to make the point, the views are persistent. So they're persistent, they're like materialized views in R. Because they're different shapes of the data, so whenever you want, you can say, okay, I need this, or I don't.
And then replace the data and actually goes the migrates that you.
That's right. Yes.
Okay, so in your model you talked about trillions of rows and okay. What about sampling? Monte Carlo, you don't have to look at every one of those 12 trillion rows. You can look at some subset of that and get it pretty good. If you know, unless you have such outliers that are absolutely going to dominate. One of the 12 trillion are going to be, you know.
Right. Well, this is a very good question. The question is, why can't you just sample the losses in an insurance model, in a catastrophe model? So I'd love to get you with our modeling development team, because they have a bunch of PhDs that will tell you why you can't do that. But I'll answer a little bit of what I know, which is basically the numbers have to add up because it's a financial instrument.
Yeah.
And that's the difficulty.
Okay, so it's a regulatory
That's
issue.
right. That's right.
A
And
legal
so,
issue. They can't say
That's right.
there's a 99.99% probability if. Okay, bingo.
Yeah, and it, you know, anyway, it curves and all kinds of other
I know
things.
about
But
regulatory.
I could get you with them, but anyway, it's a pain.
The model has to deliver a price for your house and each and every house,
You're gonna have an
and each
expert.
and every insurable object.
Oh,
that's
okay, you
going
can't
into the
sample
model
the houses, you have to.
That's right.
Has to be delivered in output.
That's right, because your contract might be good to bring in your contract. Your deductible could be different, your coverage could be different, all those kinds of things.
Yes, over
Thank
there.
you for the help.
Do you read the MySQL replication logs, or how do you tie into these third-party databases?
So the question is, does AgilData read the MySQL replication logs, and that's one of the data sources you can use? So there's all kinds of different data sources. It can be your application, it can be another database. That's one of the first things we actually started with. Yeah.
So this is like more of an insurance question, and I know the question. I'm just kind of curious because, you know, I'm sure like insurance companies, they have like data modeling and all that, right? And let's say a homeowner is completely insured, and do they run like all these complex modeling and statistics, and then they decide, okay, because of this compute model, we decide we're not going to do insurance. You know, just
Right. So the question is, does an insurance company make decisions based off these models to not give insurance? I think the main purpose of them is to be able to price the insurance so that they don't go out of business and to make sure that they're covered, right? Because an insurance company, you know, they're taking a bet that a hurricane happens every so often, or an earthquake or whatever.
One case is that when Sandy hit, water for water or sand, things like wine, greasy wine. All it was running engulfed in flames, and they had to scramble, complicated choices.
That's right. That's right. And you'll also notice that when a big disaster happens, they have a moratorium on the insurance because they have to figure out if they're going to make it or not. And the way they're doing that is they're running on models. Very typically, that's what they do. Is they stay up for days when something like that happens, and they actually figure out what the impact is going to be.
Okay. They not wait if they decide that it doesn't, that they cannot make it.
Well, the problem is, the question was, can you not wait to do that? And the problem is, for something like a big disaster like that, like Hurricane Sandy, it might be 5 years before you know what your actual losses are. So you have to know now, because also insurance companies have reinsurance companies, and they have to submit claims to them. I mean, it's a big, right? So all of a sudden, reinsurance companies are scrambling to say, well, what do I own of this? And then, it's quite something. Right?
They just fight between them, instead of just, I cannot afford it, I will not pay. They cannot say this.
That's right.
They have to go out of business.
That's correct, and it did happen, right? So all this got started because insurance companies did go out of business from Hurricane Andrew. So that's really what helped get this all going. So yes.
The question is, what can we learn and where can we read about this software project that came out not as expected and that AgilData was able to solve?
Okay, so where could you read about this? Well, you certainly can just look up RMS. We're part of a public company, and you can see what happened if you want to see the gory details. You can find out. And there are other public things that we have announced since about what's coming out soon. But I can tell you that in the next year, we're going to hear a lot more about it if you're interested. So a lot more, and I hope, over that period of time, I would like to be able to do much more open presentations about what we did, because we really did some fascinating things that I think would apply to a lot of different fields that were kind of some neat combinations of lots of different capabilities. So it's very exciting.
Question to Agile. What is the most challenging item on the table?
So the question is, what is the most challenging item on our table?
Yes.
That's a great question. For us right now, we've renamed the company. It used to be called Code Futures, and the company is now called AgilData. We still, our biggest challenge right now is, I would say, kind of on the, I'll be totally honest, it's on the marketing positioning side, right? It's not a technical challenge. We've renamed this. We're trying to figure out, I come out of the, early stage startup thing, and I'm here in a company that's older, and we're repositioning around at the next generation of what was very mature, very successful technology. We're trying to figure out how do we position it, and events like this are helping us figure that out. So it's living that agile principle and trying to get first contact with the market, getting your feedback, and that honest feedback is what we really just live and die by. So that's the challenge right now. If I had answered you from a technical perspective, I would say right now it's basically making sure we are talking to all the right systems, all the different sources of data, and all the different sinks of data to make sure that we play right in that larger ecosystem.
Sure. There are things that, how they happen, things that, how they require. And my teams, I will be the most challenging about code complexes and processing technologies was that everybody's a stream and everything is stream. When you come into actually working with streaming solutions, what you really benefit from is a tail. Because essentially, so if you really think, what happens is events happen. But what you need in the end, you need, for example, let's take JavaScript, just for instance. There is no stream definition in JavaScript. What you benefit in JavaScript, you benefit from array, or generally speaking, about from tail. So essentially, any improvements in delivering really cool solutions to market.
Let me see if I can echo that question back. You're saying that when people implement streaming processing, what they really need in some cases is a table, right? And if I could extrapolate from that, I think what you're getting at is what they could really benefit from is historical data. So you don't want to just touch each individual item by itself, because each event doesn't necessarily contain all of the meaning for you to derive useful analytics. So you need to somehow connect the real-time data with the historical data that's either present on disk somewhere, or maybe elsewhere in memory, or maybe even on another machine's memory. That's an interesting challenge, right? And that's one of the things that we're excited to do, is to maintain the historical record and connect the new real-time data with that history via, in our case, a join statement or join clause.
to join those third parties?
You can. We don't want to do that in a real-time fashion. We would prefer to keep a copy of that real-time of the third-party data, specifically because if the third party is somewhere else, you're going to pay that latency wherever that is, right? So we're going to be very honest about the best way to do it. We can get the third-party data, but it's better to get a feed of that data and have a local partitioned copy of it.
We have time for just one more question.
And I had just one follow-up comment, which is his really biggest problem is me.
Going back to RMS, does RMS or the model insurance contracts for specific locations for specific clients? And are they able to figure out which areas are the least or the most recent? And do we make that data available to public or not?
That's a very good question. Does RMS have different kinds of models for different parts of the world and regions and store that data? And do we make it available to the public? So some of it's available to insurance companies, for sure, to our customers. I don't think we have anything that's publicly available, but that is something that's been talked about, but that's not my area so much. But what I will tell you is we have what we call peril regions all around the world. So we always joke that we have a model for Guam, right? And we have a model for California for earthquakes and Alaska and all these different places, right? So you can basically take these different perils and you can actually see them all over the world. And we're constantly expanding our model portfolio. So there are dozens of models now, and there will be many, many more.
All right, who wants shirts? Hey, your hand up went first. Oh, that didn't make it there, but all right, here. Okay. I want to give a great big thank you to Cory Isaacson and Dan Lynn. They will be here for one-on-one questions. Definitely come up right now and ask them. Thank you all for coming.
By the way, if you have a shirt that's not the right size, I would suggest everyone meet in some corner and let's see if we can exchange it all and have a happy equilibrium. We'll see you soon.